Let us begin in a very quiet place, the idea that a curve has a slope at a point. The derivative at a point is a local piece of information. It describes how the function is changing right there in a tiny neighborhood around that point. When we say local, we mean we are not yet making a statement about a whole interval, or about the overall direction of the graph. We are only describing the immediate tendency of the function to rise or fall. And yet a great theme in calculus is that local information, if it is organized correctly, can tell us something global. The mean value theorem is one of the cleanest examples of that theme. It is a bridge between what happens at individual points and what must happen somewhere in between 2 points. Let us pause and reflect on the picture that motivates it. Suppose you have 2 points on the graph of a function and you draw the straight line connecting those 2 points. That straight line is called a secant line. It measures an average rate of change over the interval because it tells you how much the function's value changed compared to how much the input changed from the left endpoint to the right endpoint. It is not a pointwise slope. It is a slope across a span. Now compare that to a tangent line at a point. A tangent line is the best linear approximation to the curve at that point. Its slope is the derivative at that point. So we have 2 kinds of slopes, an average slope across an interval and an instantaneous slope at a point. The mean value theorem says, in calm and reliable words, if a function is continuous at a closed interval and differentiable in the open interval inside it, then there exists at least one point strictly between the endpoints where the instantaneous slope equals the average slope across the interval. In other words, somewhere in between, some tangent matches the secant. It is worth repeating the conditions, because they are not decorative. Continuity on the closed interval means there are no jumps or holes on the entire interval, including the endpoints. Differentiability on the interior means there are no sharp corners or cusps inside. When those conditions are met, the function is well behaved enough that the theorem must hold. You can think of it as a statement about fairness. If the function starts at one height and ends at another height, then the average climb per unit horizontal distance is fixed. The mean value theorem tells you the function cannot avoid having that exact climb rate at some moment along the way, provided it moves continuously and without corners. If it tried to avoid it, it would be forced into a contradiction with the way continuous differentiable curves behave. Let us restate the same idea in another gentle way. Imagine you travel along a road from one town to another. You know the total distance and the total time, so you know your average speed. If your speed changes smoothly without teleporting and without instant jumps, then at some time during the trip your instantaneous speed must equal your average speed. This is not an analogy that replaces the theorem, but it helps the mind accept the inevitability of the statement. Now let us pause and ask, why do we care, mathematically, that some tangent matches the secant? The answer is that it allows us to turn bounds on derivatives into bounds on the function itself, and it allows us to turn information about the sign of the derivative into information about monotonicity. Start with monotonicity, because it is one of the most useful consequences. Suppose the derivative is positive everywhere on an interval. Positive derivative means the function is locally increasing at every point in the sense that near each point the function tends to rise when you move to the right. The mean value theorem upgrades this local rising to a global rising. If the derivative is positive throughout the interval, then the function must be increasing on the entire interval. Why? Take any 2 points, left and right, and look at the secant slope between them. The mean value theorem guarantees some interior point where the derivative equals that secant slope. If the derivative is always positive, then that secant slope must be positive, so the function's value at the right point must exceed its value at the left point. This works for any pair of points, so the whole function is increasing. It is worth repeating, the mean value theorem is the mechanism that turns the derivative is positive everywhere into the function is increasing everywhere. Without the theorem, you might feel it should be true, but you would not have a rigorous bridge. Similarly, if the derivative is negative everywhere on an interval, then the function is decreasing on that interval. Again, the mean value theorem ensures every secant slope is negative, and therefore values drop as you move to the right. And if the derivative is 0 everywhere on an interval, then the function is constant on that interval. This is another quiet but profound point. If the instantaneous rate of change is always 0, the function cannot climb or descend anywhere, so it must remain flat. The mean value theorem gives the proof. Any secant slope between 2 points must match some derivative value, but every derivative value is 0, so every secant slope is 0, and so the function has the same value at any 2 points. Let us also mention bounds, because they matter in applications. Suppose you know that the derivative is never larger than some fixed number in absolute value on an interval. That means the function cannot change too fast. The mean value theorem tells you that the difference in function values between any 2 points is controlled by the derivative bound times the distance between the points. In plain words, if your slope is never steep, your height cannot change dramatically over a short horizontal distance. This is one of the simplest forms of elliptic type control, and it is the beginning of many estimation techniques. Now let us pause and reflect again. The mean value theorem does not tell you where the special point is. It promises existence, not location. That is typical in analysis. Many theorems guarantee that something must happen, even if they do not give a direct recipe for finding the point. And yet, even without location, the existence statement is powerful enough to prove monotonicity, uniqueness results, and inequalities. It is worth repeating the central sentence of this section. If a function is continuous on the closed interval and differentiable inside, then some tangent matches the secant. Local slope equals average slope somewhere. We will carry this with us, because it is one of the guiding principles behind optimization and curve sketching. Now we drift naturally into optimization, because optimization is really the art of turning derivative information into decisions about large-scale behavior. When you optimize a function on an interval, you are trying to find where it reaches its highest value or its lowest value on that interval. Let us use careful language. A global maximum on an interval means a point where the function's value is greater than or equal to its value at every other point in the interval. A global minimum means a point where the function's value is less than or equal to its value at every other point in the interval. These are global statements, because they compare one point to all points. Derivatives, on the other hand, are local. So the key idea is to identify special points for local behavior can produce a global extreme. There are two kinds of candidates. First, there are endpoints of the interval. Endpoints matter because if you restrict yourself to a closed interval, the function cannot go past the ends, and extremes often occur there. Second, there are interior points where the derivative is zero or where the derivative does not exist. These are called critical points. The name is appropriate. These points are critical because the function can change from increasing to decreasing there, or from decreasing to increasing, or it can form a sharp peak or valley. It is worth repeating the basic workflow for one-dimensional optimization on a closed interval. To find the global maximum and minimum on the interval, you list all critical points in the interior, you also include the endpoints, and then you evaluate the function at all those candidates. The largest value among them is the global maximum, and the smallest value among them is the global minimum. Why does this work? Because a continuous function on a closed interval always attains both a maximum and a minimum. That is a fundamental theorem from analysis. And once you know the extremes exist, calculus tells you they must occur either at endpoints or at interior points where the derivative is zero or fails to exist. This is because if an interior point is a smooth local maximum or minimum, the tangent line must be horizontal there, which means the derivative is zero. Let us pause and reflect on that statement. If you stand at the top of a smooth hill and you look at the immediate slope right under your feet, the slope is zero. If the slope were positive, you could take a step to the right and go higher, so you would not be at a maximum. If the slope were negative, you could take a step to the left and go higher, again contradicting maximality. So at the smooth interior maximum, the derivative must be zero. The same reasoning holds for a smooth interior minimum. But it is worth repeating a subtle point. Derivative zero does not guarantee a maximum or minimum. It only identifies candidates. A point with derivative zero could be a local maximum, a local minimum, or neither. It could be a flat inflection-like point where the function continues increasing through a horizontal tangent. So we need additional tests. This brings us to the first derivative test. The first derivative test says, look at the sign of the derivative just to the left and just to the right of the critical point. If the derivative changes from positive to negative, the function goes from increasing to decreasing, and the point is a local maximum. If the derivative changes from negative to positive, the function goes from decreasing to increasing, and the point is a local minimum. If the derivative does not change sign, then the point is not a local extreme, even if the derivative is zero. This test is intuitive. Increasing then decreasing makes a peak, decreasing then increasing makes a valley. It is a test that relies on the shape of the function's growth. Then there is the second derivative test, which uses the second derivative to measure concavity. The second derivative, in plain words, describes how the slope itself is changing. If the slope is decreasing as you move to the right, then the graph bends downward, which we call concave down. If the slope is increasing, the graph bends upward, concave up. The second derivative test says, at a point where the first derivative is 0, if the second derivative is positive, the graph is concave up there, like the bottom of a bowl, so the point is a local minimum. If the second derivative is negative, the graph is concave down there, like the top of a hill, so the point is a local maximum. If the second derivative is 0, the test is inconclusive. And it is worth repeating, inconclusive means you must use another method, not that there is no conclusion. Now let us add one more layer, modeling decisions. In one-dimensional constraint optimization, the constraint usually shows up as an interval. You are optimizing not over all real numbers, but over inputs that satisfy some requirements, such as a length being non-negative, or a time being between two bounds, or a physical parameter lying in a feasible range. In that case, the endpoints represent the boundary of feasibility. So including endpoints is not a technicality, it is part of respecting the model. And in practical problems, you often form a function that represents a quantity to be maximized or minimized, like cost, area, error, or energy. Then you use the derivative to find critical points, and you compare them with endpoints. The calculus provides the machinery, but the modeling provides the meaning. The main lesson is that the derivative identifies the turning points, and the endpoints represent the limits of the scenario. Let us pause and summarize what we have established. Optimization in one variable usually follows a repeatable method. Identify candidates, endpoints, and critical points. Then decide which candidates are maxima or minima, either by comparing values directly for global questions, or by using sign changes of the first derivative for local behavior, or by using concavity information through the second derivative. And always remember, derivative 0 marks a candidate, not a conclusion. Now we move into curve sketching, which is not a separate topic so much as a synthesis. Curve sketching is where you take many small derivative-based facts and assemble them into a coherent picture of the graph. It is worth repeating what synthesis means here. Instead of doing one computation to produce one number, you gather multiple pieces of information, and you let them constrain the possible shape of a function. You build a disciplined workflow so you do not miss important features, and you do not guess. A standard workflow begins with simple structural information. First, intercepts, where the graph crosses the vertical axis and where it crosses the horizontal axis. These points anchor the curve in the plane. Even if you do not draw, you can still describe them as places where the function takes the value 0, or where the input is 0. Next, asymptotic behavior, how the function behaves far to the left or far to the right, and what happens near points where the function is not defined. This tells you about vertical asymptotes and horizontal tendencies, and it helps you understand the boundaries of the graph's domain. In common words, you want to know if the function shoots upward or downward near certain inputs, or if it levels off, or if it grows without bound. After those structural pieces, you bring in the first derivative. The first derivative tells you where the function increases and where it decreases. You find critical points where the derivative is 0 or undefined, then you test the sign of the derivative between them. This partitions the domain into intervals where the function is consistently rising or consistently falling. Let us pause and reflect. This is essentially the monotonicity consequence of the mean value theorem in action. If the derivative is positive on an interval, a function rises on that interval. If the derivative is negative, it falls. So a sign chart for the derivative becomes a reliable guide to the overall direction of the graph. Then you bring in the second derivative to talk about concavity. Concavity is about how the slope changes. If the slope is increasing, the curve bends upward. If the slope is decreasing, the curve bends downward. This affects the shape in a deeper way than just rising or falling. Two functions can both increase, but one can increase while flattening out, bending downward, and the other can increase while steepening, bending upward. The second derivative distinguishes these. Where the second derivative changes sign, the concavity changes, and that suggests an inflection point. An inflection point is where the curve switches from concave up to concave down, or the reverse. It is worth repeating, an inflection point is not merely where the second derivative is 0. It is where the concavity changes. The second derivative being 0 is a candidate condition, much like the first derivative being 0 is a candidate condition for extremes. So curve sketching becomes a layered narrative. You start with where the function lies and where it is anchored. Then you describe the rising and falling behavior from the first derivative. Then you describe the bending behavior from the second derivative. And finally, you combine these to produce a coherent picture of peaks, valleys, flat points, and the way the function approaches asymptotes or infinity. Let us pause and summarize again, because repetition helps the mind settle. A disciplined workflow might sound like this: identify intercepts and domain restrictions, check asymptotic behavior, find critical points from the first derivative, use the sign of the first derivative to mark intervals of increase and decrease, then examine the second derivative for concavity and inflection points, and then assemble a consistent shape. At each stage, you are not drawing randomly. You are justifying the shape with derivative information. This is why curve sketching is a synthesis. It uses optimization, monotonicity, and concavity together. And it also prepares the mind for later topics, because the language of increasing, decreasing, concave up, concave down, and inflection points appears repeatedly in analysis, differential equations, and applied modeling. Now we turn to antiderivatives, and the shift is gentle. Up to now, we have focused on differentiation and what derivatives tell us. Antiderivatives begin the process of reversing that operation. An antiderivative of a function is another function whose derivative gives back the original function. In plain language, it is a function that, when differentiated, produces the given function. This is the sense in which antiderivatives undo differentiation. It is worth repeating the most important conceptual point: antiderivatives usually come in families. If one function has the correct derivative, then adding a constant gives another function with the same derivative, because constants disappear when you differentiate. So antiderivatives are not usually unique, they differ by constants. This is why, when you find an antiderivative, you typically talk about a whole family of solutions. You are not just finding one curve. You are finding an entire vertical stack of curves that are identical in shape, shifted up or down. Let us pause and reflect on why this makes sense. The derivative measures change. If you shift a function upward by a constant amount, you do not change how it rises or falls, and you do not change its slope at any point. So all vertical shifts share the same derivative. Therefore, when you reverse the process, you cannot recover the absolute vertical position from derivative information alone. You can recover the shape, but not the vertical offset. That missing information is precisely the constant of integration, expressed in words as an arbitrary constant. A common practical habit with antiderivatives is verification. Because integration, when done by rules and techniques, can be error-prone, it is common to check your answer by differentiating what you found. If differentiating your candidate antiderivative returns the original function, then you have succeeded. This is a quick verification, and it reinforces the idea that differentiation is the forward operation and antiderivatives are the reverse. It is worth repeating: you can always check an antiderivative by differentiating. This check is often simpler than the original antiderivative problem, so it becomes a reliable way to build confidence. Now, although we are not using formulas here, we can still describe typical patterns. When a function represents a rate of change, an antiderivative represents an accumulated quantity. If a function is a velocity, an antiderivative can represent position. If a function is a growth rate, an antiderivative can represent total growth. In each case, derivatives turn quantities into rates, and antiderivatives turn rates into quantities. Let us pause and connect this back to our earlier themes. The mean value theorem linked local slope to global change across an interval. Antiderivatives will later provide another kind of link between local rates and global accumulation. Even without writing symbols, the conceptual movement is similar. Local information, organized properly, yields global conclusions. Let us pause and reflect one last time and gather the main ideas slowly. We began with the mean value theorem, the quiet statement that for a continuous and differentiable function on an interval, some tangent matches the secant. The instantaneous slope equals the average slope somewhere in between. We repeated that because it is a bridge from local derivative information to global behavior. From it, we drew consequences. If the derivative stays positive, the function rises throughout. If the derivative stays negative, it falls. If the derivative is zero everywhere, the function remains constant. And we saw how bounds on derivatives control how much a function can change. Then we moved into optimization, where derivatives help us locate candidates for maxima and minima. We emphasize critical points and endpoints, because global extremes on an interval must occur among those candidates. We repeated the idea that derivative 0 indicates a candidate, not a conclusion. We discussed the first derivative test, using sign changes to detect peaks and valleys, and the second derivative test, using concavity to classify local extremes when possible. Then we treated curve sketching as a synthesis, a disciplined assembly of intercepts, asymptotic behavior, critical points, monotonicity, concavity, and inflection points. The first derivative tells whether the function rises or falls, and the second derivative tells how the rising and falling itself changes. Step by step, the shape becomes justified rather than guess. Finally, we turn to antiderivatives, the process of undoing differentiation. We emphasize that antiderivatives form families differing by constants, because constants vanish under differentiation. And we return to the concavity verification. You can check an antiderivative by differentiating it. It is worth repeating the unifying theme in all of this. Calculus is a conversation between local and global. The derivative is local information, a slope at a point. The mean value theorem shows that local slopes must reflect global change somewhere. Optimization uses local slope behavior to locate global extremes. Curve sketching uses local slope and local bending to build a global picture. And antiderivatives begin the reverse journey from local weights back to accumulated quantities and families of original functions. Let us end with that idea of resting quietly, local change, global behavior, and the steady logic that connects them.